Welcome back, everybody, and I hope you had a great weekend. There's one message which I wanted to give you before we begin, and that deals with the wrapping up of the project. So I need still 1 or 2 days, but since you guys are going to meet on Thursday to work on a project, hopefully the material which we will cover today can aid in getting started with a project. So the topic which we are going to deal with today is the introduction of a quantum mechanical system, which allows us, without not too much pain, whatever that means, we can actually rewrite the Hamiltonian in terms of Pauli X, Y, and Z matrices, or the sigma X, sigma Y, and sigma Z's. And that's because we are going to introduce something which is called the variational quantum eigensolver. And that is a method which works best with Hamiltonians that can be written as a sum of polynomials of Pauli operators and their tensor products. The simple Hamiltonian, which we looked at some weeks ago, 2 weeks ago, was a Hamiltonian where we rewrote the Hamiltonian matrix in terms of tensor products of Pauli X and Pauli Y and Pauli Z matrices. And this is a clear an example of such a system. It's also a system which contains a lot of the basic many-body physics. So the type of many-body problem which we're going to look at now may be something which some of you have not encountered before. And I know that those of you coming more from computer science, the linear algebra part is something which may have been familiar to basically all of us. But now we need to be a little bit more physics specific. And we are going to link this model to a specific interpretation, and we're going to rewrite it in terms of what is normally called creation and annihilation operators. So right now, for those of you who are not too familiar with quantum mechanics, this is going to be a quantum mechanics day, where we now dive into more technicalities about the way we would rephrase a Hamiltonian in terms of something which is called second quantization. Now, second quantization is very, very beneficial when we are rewriting Hamiltonians, and I'm going to explain why. One of the main reasons, if you're thinking of systems like fermions, when we now are looking at a specific state, second quantization, you can actually read that as the occupation formalism, or sometimes it's also called the number formalism. So instead of dealing with all the degrees of freedom, with the spatial degrees of freedom and particular quantum numbers which are coupled with those, we are now thinking of an abstract basis, which is called a Fock basis, an FOCK, just to avoid misinterpretations. And this basis is a basis where we now take away the spatial degrees of freedom, and they will be incorporated in integrals or constants of the interactions. And then we introduce operators which allow us to express in a more compact way many-body states, and also the way we interpret many-body operators. So I'm going to give some expressions which, to a certain sense, require that you have taken a course in more many-body physics or more advanced quantum mechanics. But I hope that the basic machinery which I'm going to give you is something which will allow you to become operative. At the end, what we end up with is a Hamiltonian which is written in terms of Pauli X, Pauli Y, and Pauli Z matrices. And that is the Hamiltonian which we are going to feed into the quantum eigensolver. So if you can, or willing, if you haven't taken a course, let's say in advanced quantum mechanics, like physics 4110 or physics 4480, which deals with many-body physics, I hope the kind of overarching message is something which will allow you still to understand what is going on. But we need to go through these technicalities because the focus in this specific course is going to be on simulating quantum mechanical many-particle systems. And the Lipkin model, like the quantum mechanical easing model or the Heisenberg model, these are models which can all be rewritten in terms of Pauli X and Pauli Y and Pauli Z matrices, which then makes it much easier to set up the relevant gates and use all the machinery which we discussed last week with Qiskit. So feel free to ask questions, and we may probably have to continue with this topic next week, and let's see how far we get today. So the first thing which I'm going to do now is to introduce this Hamiltonian. It's called the Lipkin model. And the Lipkin model was introduced in actually nuclear physics as a model which now takes into account the different types of excitations. And it's a model which has analytical solutions for some of the cases. And it also allows for analytical solutions of an approximative many-body method, which is called Hartree-Fock theory. And we are going to look at a system where we can have two or more interacting fermions. So the model can actually be generalized to an infinity of fermions, actually. And in order to set up the model, I'm going to switch a little bit back between the whiteboard and the slides here. So the example which I have here is an example with the 4 particles, which can occupy 2 single particle states. And these single particle states are set up with their own energies. And you can think of these single particle states as a computational basis for us. And later we are going to introduce a 4 particle basis as the computational basis. So the best way to visualize this model is actually to make a drawing. So let's do that. So let me bring this up. And some of you have actually seen this model before in a course like Physics 480, where this is one of the weekly exercises. So if we now want to study the Lipkin model, we can make a figure here where you now can think of a so-called 2-level system. And this 2-level system is a little bit different from what you may have seen before. So we're going to have an energy here, an epsilon 0, which is just given by some constant minus epsilon 1/2. And then we have an energy level here, which is given by just a constant. So these are just constants which I'm making up here. The thing with this model here is that if we now look at n equal to 4 fermions, and I'm coming back to fermions, the system here can have eventually all fermions in this specific state. So this state has a degeneracy of 4. And these are going to be states where the particle is distinguished by having just spin down. So that could be one way to arrange 4 fermions here. Alternatively, you could now think of having the system, and I'm just writing this in terms of 0 and 1. So these are the states, epsilon 1 and epsilon 0. We could have a system here, and this is now particle 1, 2, 3, and 4. We could have a case where we now have 2 fermions in the lowest lying state, 1 and 2 here. And then we have 2 slots here where the spin points up. And these are slots 3 and 4. So these particles are now labeled by where they are. So this epsilon 1 is something which is going to take a subscript P. So this Ep1 here, and the same with this P here. And we're going to put a label on this one in depending on where it is placed, whether it's in the state with spin up or spin down. And it means that when we now label single particle states, we are going to need to classify in which single particle level it is. and which spin state it has. So the single particle level, level P, and spin, which we're going to label with a sigma spin in the notation here, denote a single particle state. So if you now look back at the, sorry, I just touched that one. So these states here, 1, 2, 3, and 4, they are now going to, so this number P now is going to be given by these numbers 1, 2, 3, and 4, which we then will classify in which single particle slots the particles are. And then it's going to have a spin, which we are going to label with either a spin up or a spin which is a spin down. And these are normally given by the numbers 1/2 and -1/2. So a single particle state is going then to be identified by the states P and sigma, or these labels. And we are going to rewrite that in terms of so-called creation and annihilation operators. So that means that we are going to have a state P of sigma, and this is an operator, which then acts on a vacuum state 0. So what I'm doing now is, because I know that most of you have taken a course in many-body physics, so you've seen this second quantization formalism. And for fermions, what we are going to deal with then are creation and annihilation operators. Which we're going to label with an AP sigma. And then we have the annihilation operators. AP sigma like this. And they have anti-commutation relations. So it means that if I take AP sigma, so let's just write them down. I'm not going to derive them. If you want to see the derivation of it, you can actually go into my lecture notes in many-body physics, which is called Physics 4480, and you will actually see the derivation of the creation and annihilation rules. So the thing is that now we are going to represent a given state, not in terms of all the quantum numbers which specify a state, like the spatial quantum numbers, the angular momentum quantum numbers, and so on. But we are going to replace that in an abstract space where we simply count the number of particles which are in a given state. So you can think of this P and sigma here as specific slots. So if you go back to the state which you have here, you could now say that we label this simply with a state 1. And that state 1 tells us immediately what are this specific slot, tells us immediately which quantum numbers we can actually identify that specific state with. So this AP sigma plus here is now going to be defined by the way we operate with. So we have an AP sigma here. This is the anti-commutation relation, and that is given by AP sigma dagger AP sigma plus an AP sigma, and this is equal to 0. We also have the anti-commutation rule for the annihilation operators, which also reads AP sigma times AP sigma prime plus AP, so instead of a minus, which are used to when you have a standard matrices and you look at the commutation rules for a matrix. These are called anti-commutation rules. And we have a prime, AP sigma, and this is also equal to 0. And then we have the final anti-commutation rule, which involves a creation operators and an annihilation operator. AP sigma And if we now just label these as a collective parameter I and a collective parameter J, so you see now that these different quantum numbers can be collected in terms of given slots, and every slot points to specific quantum numbers. And that gives us the possibility to encode a many-body state as a string of bits. And this string of bits allows us then, for the fermionic case, to make a pretty straightforward link with the quantum computing and the bit representation. So you could now think of these being represented by specific qubits, as an example. And this anti-commutation relation is then given by the Kronecker delta. So if the particle is in the same state, then these operators actually commute, anti-commute. Now, we can also identify a many-body state. Actually, I was a little bit rushed here because I should have been a little bit more. So I'm going to put in slots here. I was a little bit too much in a rush here. So this would be slot 5, 6, 7, and 8. So that means that in the case which you see here, we would actually identify this in terms of a single particle state 7 and 8 here. So for the lowest lying state, we can have fermions in the states 1, 2, 3, 4. So this is, if we go back to this state, so for fermions, we express a many-body state. And this is expressed in terms of these creation operators. In terms of the creation operator, AP sigma dagger. So what we would have then is the following. So the ground state, or these ansatz, where we have all particles in the lowest lying state. So this specific ansatz which you see here. This is a state which we could now write out, if we assume also that this is the lowest possible state. So we could now write this out as a phi 0, which is given by A of 1 spin down dagger, A of 2 spin down dagger, A of 3 spin down, and A of 4 spin down dagger acting on 0. This is often written now in a more compact way as 1 spin down, 2 spin down, and then I have 3 spin down, and then I have 4 spin down here. So that means that we have actually occupied different slots. And if you now want to do the relabeling of these states, you could now think of the first slot as being slot 1. And slot 1 means that it has this number p equal to 1 and the spin pointing down. And then slot 2 would be the equivalent one with particle, with p equal 2 and spin down, etc., etc. So this is a way by which you would now encode a given computational many-body state. So this is a computational basis. For a many-body state. So the kind of way which, when you're now using second quantization, is that we have actually taken away the spatial degrees of freedom, and we keep only the degrees of freedom which now represent which specific slot is being occupied or not. So when I act, if we now make this a little bit more general and we take away the spin degrees of freedom, so what we're going to have is a more general state. General state is now going to be given by a state phi, which is simply the product of all the slots which a given particles are occupying, up to n minus 1 particles. And then I would have these creation operators AI dagger acting on the true vacuum state. So a general state then, a 4-particle state. So let's take that as an example. A 4-particle. So this is just a mapping of what some of you may have seen in what is called first quantization in terms of a Slater determinant. So one way to represent the anti-symmetry of a many-body fermionic state, so a state which is based on fermions, interacting fermions, or non-interacting fermions, is to rewrite the trial wave function as a determinant, and which is a determinant which is normally called a Slater determinant. So a 4-particle state then, if we now simplify a little bit and take away the spin degrees of freedom, would now be given by phi equal to an A1 dagger, an A2 dagger. I should actually put this one, let me just rewrite it and just start the summation from 1. A3 dagger, A4, and this is equal to 0. Now to acting on 0. And this is normally rewritten as 1, 2, 3, and 4. And if you want to convert that one into a bit string, if you have 4 particles, then you will simply now have bit 1 if state 1 is occupied, bit 1 if state 2 is occupied, bit 3 if state 1 is occupied, and bit 1 if state 4 is occupied. Then we have also the kind of calculation of rules that if I now act with a annihilation operator on these states here, so if I have an AP acting on this state here, then this is equal to 0 if P is not equal to this one of the states 1, 2, 3, and 4. So if P is given by one of the states, then what it means is that we are taking away a particle from one of these specific slots. And that means that AP, this annihilation operator acting on this specific state, what that explicitly means is that we are going from a 4-particle state to a 3-particle state. We can also have operations of the type of AP dagger, of AQ, acting on this state phi 0, phi. And this state is also equal to 0 if this Q is not contained into 1, 2, 3, 4. And if the state P is actually equal to one of these 1, 2, 3, and 4. Because if we have AP acting on the state 1, 2, 3, 4, if the state is occupied, we cannot put in more than one fermion in a specific state. So this is equal to 0 if P is equal to 1, 2, 3, and 4, one of these combinations. So this allows us to really write in a very compact way the operations of these operators on a specific state. The thing which is nice as well, and this is used in most of many body physics codes, is that it allows a very compact way to encode information in terms of bit string. So every state is a bit string, depending on which states are occupied and not occupied. So suppose now that the system has accessible a given set of states. So suppose now P is a space which is given by states up to a given number, n. So what happens then is that we would have a given number of slots. So each P is a slot which points to specific quantum numbers. So if you're using a bit encoding here, it means that every one of these, if they are occupied, that means that we can then produce a state now which has a given bit string as a representation. Suppose now that n is equal to 8, just to give you an example. So that means that we would have 8 slots. One, two, three, 4, 5, 6, 7, and 8. And if we now have 4 particles in the specific system, and we can distribute these 4 particles in these 8 slots, then a given state could now be given by phi of, which is given by A1 dagger, and then I have an A3 dagger, I could have an A6 dagger, and then A8 dagger acting on 0. And that would be a state which we could label in a compact way, like 1, 3, 6, 8. Or alternatively, as a bit string. And since we have 8 slots here, we will need 8-bit, which means that in turn that we could now represent this state in this specific notation. So we have 1, so bit 1 means that the state 1 is occupied. We have nothing in state 2. We have a 1 particle in state 3. There is nothing in state 4. There is nothing in state 5. And then we have 1 in state 6. There is nothing in state 7. And then we have 1 in state 8. So this could be, this is normally a very effective way by which you can encode the way you can distribute the particles in different slots here. Okay, so that was a little bit about the second quantization and the way we represent quantum mechanical states. Now, the spatial degrees of freedom, which we have omitted here because we are simply looking at the number of particles occupying a specific slot. And with fermions, you can either have 0 particles or 1 particle. So you cannot have more than 1 particle in each slot. This is a consequence of what's called the Pauli principle, which says that for particles with half-valued spins, the total wave function has to be antisymmetric. Now, a consequence of this antisymmetry requirement is that the wave function, if you represent that in terms of the product of single particle states like we're doing now, it means that each such slot here can only be occupied by 1 particle at a time. And that's why we have either bit 0 or bit 1. If we are going to systems of bosons, which are quantum mechanical systems with the integer spin values, then we can have more than 1 particle in each slot. And that clearly complicates this kind of bit representation of a state, because we can have in principle, an infinity of particles which occupy slot number 1 in the example here. Now, one of the reasons why the second quantization formalism is so handy is not only that you can represent it in terms of these bit strings and you can perform bit operations. So you can actually, when you're now acting on the different states with the creation and annihilation operators, you can utilize all the strength for Boolean algebra. But the other thing is that it links very well with the quantum computing approach, which we have been discussing now, where specific states are now represented by qubits, either 0 and 1, or more complicated representations of these. So there is a very nice connection between second quantization and the formalism which we have been studying till now. However, the thing you should keep in mind now is that this kind of machinery, which you see now in terms of creation and annihilation operators, does not lend itself easily to translating a Hamiltonian in terms of this poly X and poly Y and poly Z matrices. So we have to perform specific mappings for the creation and annihilation operators to these poly matrices and these other matrices, which are normally used when we do quantum computations. So unless you're dealing with quantum information algorithms, where you don't need to bother about a quantum mechanical operator, then you can just simply keep using the gates which we have been discussing in the previous weeks. But now we need actually to rewrite the Hamiltonian. And this is the kind of exercise we are going to do now. So a general Hamiltonian with a two-body Hamiltonian. So that means that you have a two-body operator which acts between two particles at a time, is now written out in second quantization in the following way. So a general two-body Hamiltonian. So let me just state that one. And then we're going to look at the special case of the Lipkin model, which we write as an H, is often written out in terms of a one-body term. And this one-body term can often be a term which has as an eigenbasis the single particle computational basis states. And then we have an interaction piece, which is given by an HI here, I for interaction. This H0 is normally written out in second quantization. And if you want the derivation of these operators in second quantization, you can go back to my lecture notes in Physics 448, and you will see a detailed rewrite of the operators in what's normally called first quantization, where we have all the spatial degrees of freedom included. You can just use the spectral decomposition theorem and then rewrite the operator in terms of the creation and annihilation operator. So if you're interested in the mathematical development of the expression which I'm just setting up now, you can go to the lecture notes in computation or in many-body physics. So you would write this out. So P and Q stand now for one of these possible slots. This kind of collective way of encoding the information of the quantum numbers which a single particle state can have. And there is going to be a expectation value here, an epsilon PQ or transition probability. And this is given by AP, AQ, like this. This is the one-body operator. And this epsilon PQ is given by an integral. And this is where we have all the spatial degrees of freedom baked into the expression for the operators in second quantization. So this is actually an integral where we now have a single particle state P, and then we have an operator H0, which acts on a single particle at a time of Q here. So this is in principle, a multidimensional integral, where this tau can contain spin degrees of freedom as well. So it's not only an integral, but it can also contain a summation of a spin degrees of freedom or discrete quantum numbers. So I'm just leaving this kind of things out, but just remind you that this is now a state P complex conjugate of this tau, which can contain both spatial degrees of freedom and spin degrees of freedom and other degrees of freedom. And then there's an operator H, which now acts on these quantum mechanical degrees of freedom, and then multiplied with the state Q like this. So this is an integral which we now are assuming has been pre-calculated. So we are not going to deal with the spatial degrees of freedom because these integrals have already been pre-calculated. So this is a pre-calculated quantity. That means that we just have a table where we transfer the indices P and Q, and then we can simply look up a number. Then what we are having is the interaction piece, and its general form, when we are dealing with so-called anti-symmetrized matrix elements, is a free sum over these different slots, P, Q, S, and T. And this contains now a matrix element, PQ, which I'm going to write down here. And there can be an interaction, V, which acts between two particles at a time. And this contains an S and T here. And it's normal to write this as an anti-symmetrized matrix element. So I'm going to define it just in a few moments. And then I have these creation and annihilation operators. Now, since these are fermions, this T comes before S, and that has to do with the anti-symmetrization. So this specific matrix element now is again an integral over degrees of freedom. So this AS contains matrix elements which express the application of the Pauli principle. So minus, and then I have interchanged Q and P. This is P of V, S, and T. This is an anti-symmetrized matrix element. And one of these integrals, PQ, if we write it down here, V, S of T, is equal to an integral over d tau 1. And then there's an integral over d tau 2, where tau 1 is defined in the same domain as tau 2 here. We haven't specified the domain. And this contains now an integral over the quantum numbers with states defined by tau 1 and then tau 2. I have an interaction which depends on tau 1 and tau 2, and we haven't specified the interaction, but normally it's an interaction where you often have something which depends on the relative distance between two particles. That's the most common interaction you have for all physical laws, especially the energy conserving laws. And then we have an S, and this has a tau 1, and then I have a T, and then a tau 2 here. So this is the integral which we end up having to evaluate. Now, this is also pre-calculated. So you can view this as a pre-calculated quantity. That means that we are just looking up a table and we are fetching matrix elements. And that's one of the strengths of second quantization, is that if you have a table of pre-calculated matrix elements, or you can calculate them on the fly without too many problems, then you can actually store these matrix elements and then avoid the need to pre-calculate the matrix, to calculate the matrix elements. So if you look back now, what we have is a general two-body Hamiltonian operator, which can be written out in terms of two terms. One, which just contains a one-body operator, since it acts on one particle, it can destroy one state, and then it creates one state. So this is a one-body operator. And what you have here is a two-body operator, because it acts on two particles at a time. Often, this is pretty common in many-body physics. If a single particle basis is a good ansatz for a many-body system, then you would often define your computational basis as an eigenbasis of this operator H0. That means that these quantities which you see here, this epsilon PQ, they would be the eigenstates, the eigenvalues of this operator H0. And that means that you can, if you have a model like the harmonic oscillator, for instance, then we have nice analytical expression for these quantities here. And then P and Q would be a eigenbasis of H0, which means that since it's an eigenbasis, this has also to be orthogonal. And that means that that specific matrix element here reduces to a Kronecker delta PQ times a constant. So these are just small digressions here. So this is a little bit about the way we are going to represent the states. Now, what I'm going to do now is to go back to this Lipkin model, because, and before we take a break, so if we look now at this specific model which we have in mind, what we are going to look at now is one example with 4 particles. So you could now think of having 4 particles in this lowest line state. And then your Hamiltonian can now excite. So you could assume that this is an ansatz for the ground state. Then you could think of an excitation here where you promote, let's say, one of these up here. So you actually flip the spins. So you leave this place vacant. And then you leave the 2 other remaining particles down here. So this would be an example of what we normally call a particle hole excitation. So you leave a hole in the state here, and then you create a new state up here. So this is one type of excitation where you actually act on one particle at a time, which you could bake in your interacting part of the Hamiltonian. You can have many other such cases. So, but since you act only on two particles at a time, another type of excitation which you could have would be one where you start with the same state here, and then you move to a new state where you have now promoted two particles up here, which is a state which has a larger single particle energy. So we would call this an excited state. And then we're just leaving two slots empty here. And in this specific case, we would now have, if we now insist on these labels, so this will be 1, 2, 3, 4. What we are going to do is actually to use these labels 1, 2, 3, and 4, since we classify the states in terms of the spin quantum numbers. So this would actually be state 3 with a spin up and state 4 with a spin up. Alternatively, we could have called these slots, these additional slots here. If we now want to take away the spin degrees of freedom, we could simply have called these slots 5, 6, 7, and 8. Or we can use the spin degrees of freedom, and that means that we would have to explicitly define which spin state the system is in, or the single particle state is in. And that means that we would keep this number p equal to 3 and p equal to 4, and change the spins. So this is a 2 spin flip state, and you could think of this one as a 1 spin flip state, or 1 spin flip excitation, which is a better wording. And this other one would be a 2 spin flip excitations. Or if we now define a Fermi level here, we can think of the states below the Fermi level as when we excite up one of these single particle states as leaving a vacancy here, or just a whole state. And you could think of this state which you see here, the new one, as a 2 particle, 2 hole excitation. So you leave 2 holes here and you promote 2 particles up here. So this is often called in many body language as a 2 particle, 2 hole excitation. And this is called as a 1 particle, 1 hole excitations. This is jargon. This is a kind of language which we often use in order to define in a more compact way a given type of excitation. So the difference between the standard first quantization and second quantization is that now, compared to first quantization, where you let the particles interact an infinity of times, we are now going to represent all the possible states the system can be in terms of an infinity of particle hole excitations, or these type of excitations as we are defining here. So in our case, since we only have a limited number of states, you see now that the total number of states which we can make is given by a combinatorial exercise with replacement. Total number of states, number of states in our case is equal to 8. And if we have a case with 4 particles is equal to 4, then the total number of ways we can distribute, total number of configurations or way we can distribute the particles of configurations is given simply by a combinatorial factor. So this is a binomial factor of 8, 4. So which is obviously 8 factorial divided by 4 factorial divided by 4 factorial. So this is the same as 5, 6, 7, 8 divided by 2, 3, and 4. So we take that one away and we have this one and we have 2 here. So this is 10. So we are left with 70 states. This is a total number of states which we can make. However, as we will see after the break, there are only specific combinations which are interesting because the Hamiltonian preserves specific symmetries. So let's take a small break. So this Lipkin model is an example of a quantum mechanical Hamiltonian, which we now are going to look a little bit closer in terms of the details which we need in order to set it up and perform our first calculations here. So the model and the calculations which I'm showing here are tailored to a system with 4 fermions, but the model which we will implement ourselves first is actually defined in terms of only 2 fermions. So the model is very flexible. And what we have now is a, as we said, a state defined by 2 quantum numbers, plus or minus 1. And then we have these additional quantum numbers, 1, 2, 3, and 4. So that means that a given single particle state is going to be classified by the spin value with spin up or down. You can label this as -1 or -0.5. This is actually twice the value. And you would typically write it like this, or you could even put up the spin values if you want to. The Hamiltonian, on the other hand, is now going to be written in terms of 3 terms. One term, where we now run over the spin degrees of freedom here, and we have a creation and annihilation operator. And this, as you can see here, for the creation and annihilation operator is going to be diagonal in sigma and p. And there's a constant epsilon, which then defines a constant energy. Then we have an interaction piece, and in the case which we are going to look at first, I mean, down in the slides here, you will find a case where we put this W equal to 0. So V and W are constants. And this operator H1, which we have here, that moves 1 pair of fermions, while H2 is normally what we call a spin exchange term. That means that the latter moves a pair of fermion from one specific state, where you have a P prime and minus sigma, to a state where you have P minus and P prime and sigma. So we're just exchanging the spins. We are going to, here, we're going to deal with a full Hamiltonian in terms of this H1, H2, and H0. But in the first attempt for the project, we are going to leave out W. So we are going to rewrite. The thing which is nice now is that we can rewrite this Hamiltonian, which you see here, in terms of operators for quasi-spin. And this J plus and J minus and JC. JC is going to be given by the Pauli Z matrix. And similarly, we are going to rewrite J plus and J minus in terms of the Pauli X and the Pauli Y matrices. So the Hamiltonian can be rewritten in terms of these quasi-spin operators. And that's one of the nice things, because it allows you to also set up the Hamiltonian matrix by using raising and lowering operators. The other thing which is nice is that it also gives you a very easy way to show that the Hamiltonian here conserves the total angular momentum. It's going to commute with the J squared. And J squared is actually this operator here. And I'm just reminding you of some of these definitions from basic quantum mechanics. I know that some of you have never seen this before, but I hope you can accept what is coming. I put up all these equations here so that you can have them for the sake of completeness, and you see the transformation. Because when we get into a general many-body operator of the one-body and two-body type like we have here, we have to deal with more convoluted and more complicated transformations, and that's normally given by something like a Jordan-Wigner transformation. But here, we can actually map this operator here, which is written in the standard quantum mechanical way in terms of creation and annihilation operators. We can just rewrite it in terms of so-called quasi-spin operators. And the way to see that is as follows. So you can also, for the full Hamiltonian, you need also what's called a number operator. So this simply, when you act on this on a given state, it has an eigenvalue, which is given as the number of particles which are present. So we are going to set up the following definitions for these operators in terms of creation and annihilation operators. And we have a J plus minus and a JC. And then we are going to see that this J squared can be written out like this. So in the slides here, what you will find is the actual derivation of these quantities. And what we want to do then in the first step is actually to show that we can compute the commutators, and we can relate these to the standard commutation relations for angular momentum. So I know that those of you who are here now, you have seen this before, but some of you have not seen it before. This is something which is going to be extremely useful for us when we're now rewriting this Hamiltonian. So in the slides below here, and I'm not going to go through these kind of derivations, but I provide the demonstrations of these relations, which you see here, where I'm simply writing out the different commutators in terms of the creation and annihilation operators. So if you scroll down, there's a lot of very, very exciting algebra here, which you can go through. And when you scroll down, you can actually see that this JC, J plus minus, leads to, when you rewrite the terms, it leads to plus minus J plus J minus, which is one of the commutation relations. And then you can continue with the next commutation relations, and then you have J plus and J minus. So this is just a manipulation of these expressions and using the anti-commutation rules for fermions. And then when you use those, you can then simply get the other famous relation, which links the J plus and the J minus operators with 2 times JZ. And then it's pretty straightforward to show that J squared with J plus and J minus, where you use the relation which you may have seen before for the, when you have more than 2 operators, you can actually rewrite these using these famous expressions. And then you simply obtain the relation that J squared with J plus is equal to 0, J squared with J minus is equal to 0. So these are the standard results which you should get if you can interpret this as a spin operator. And then finally, the final relation with J squared and JZ, which gives you equal to 0 here, as it should be. So that means that when you sum this up, you have all these commutation relations where we now, what we did was actually to assume that the operators, if we go back here, we could write these operators in terms of creation and annihilation operators. So with that definition, we can then demonstrate that these operators, which we have here, they obey the standard commutation relations for spin operators. They are normally called quasi-spin operators. So the next thing which we can do then is actually to go down here and rewrite the Hamiltonian in terms of these quasi-spin operators. And that's going to give us a very compact expression for the Hamiltonian, which is the one we will use in quantum computations. Okay, so what we have, if we now go back here, so we have a Hamiltonian which takes this specific form. So this is the way we've defined it. It's not the full Hamiltonian because we have only singled out specific states which can be produced by the action of the Hamiltonian. And then we rewrite the Hamiltonian in terms of the above quasi-spin operators. And also we need the number operator, in particular for this operator H2. So H0 is something we can readily identify if you now look back here. So if you look at H0, that contains a P sigma and a P sigma here. There's a sum of the spins. And if we look at the definition of the operator which we had for JZ, this is something we can identify immediately. So you see that JZ has a sum over the spins multiplied with this operator. So the only thing which is missing is this operator epsilon. So that means that we can rewrite this operator H0 simply in terms of JZ. So that's a pretty easy thing to do. And then if we move to H1 and we use the anti-commutation relations above there, we can actually rewrite that one in terms of the quasi-spin operators. So we are now getting at an expression which goes like 1/2 of J plus J minus squared. And it's pretty easy to see that by manipulating these expressions. So if you're a little bit in doubt, you could just go through these operations which you see here. And these are just the boring exercises where we simply use the anti-commutation relation for fermion creation and annihilation operators. So this is not an exciting exercise, but I'm including it here for the sake of completeness. So you see how we can actually move into these expressions here. And finally, the last term is a term which you can rewrite. When we do all these exercises, you can rewrite it in terms of the number operator, which has as a quantum numbers the number of particles present in a given state, plus this J plus minus and J minus plus. So we actually have a Hamiltonian now which can be written in terms of these quasi-spin operators, which in turn can be written out as products of sigma X, sigma Y, and sigma Z matrices. And that's extremely powerful. So you can also show, and I'm just going to state this now, that this Hamiltonian commutes with J squared. That means that J as a quantum number is a so-called good quantum number. That means if you find the eigenbasis for H, this is also an eigenbasis for J. This has the important consequence that the Hamiltonian which we have can be separated in blocks of good quantum numbers. So if you remember back before the break, we said that we had 70 states which define our system when we allow the particles to be placed in these different slots. However, we can actually reduce this dimensionality of 70 by 70 to smaller blocks because there are specific quantum numbers which are conserved. And in this particular case, then, you can define or calculate and show that the H commutes with J squared. So there's a similar exercise here, because when we have written out the operator in terms of these specific quasi-spin operators, it's pretty easy to use the commutation relations for quasi-spin operators and simply show that it actually commutes. So there's an exercise here. It's not that exciting, but you can actually show that this is the case. Then the next one, so this is just a tour de force of quantum mechanical applications. You can then use the raising and lowering operators, because if we take now a spin J equal to 2, this means that you have 5 spin projections. So you have spin projection -2, -1, 0, 1, and 2. And since we have 4 particles, you can have a total spin J equal 2 and a projection -2. This will be the lowest state, where we have slot 1 filled with spin down, slot 2 filled with spin down, slot 3 with spin down, and slot 4 with spin down. This is a unique state. You cannot make other spin combinations of that. You can then, and this is a standard trick which you may have seen before when you took a course like Physics 3.1.10 or the first standard course in quantum mechanics, when you encountered the lowering and raising operators. So there's a lot of, behind what we are doing now, there's a lot of basic quantum mechanical operations which allow us to then set up the state. So the lowering and raising operators are these famous operators here, and they relate to the so-called Clebsch-Gordan coefficients, which recouple 2 particle states into a final angular momentum or orbital momentum. And we know that when J equal 2, we have the rule that the degeneracy is given by the 5 states with different projections, JZ. And that means that the Hamiltonian matrix for J equal 2 is going to be a 5 by 5 matrix, because I can construct 5 states here. So you see now that I would have a state with the JC plus 1. So you can construct all other states using the raising operator on the first state, which is uniquely defined, because there's no other way you can actually define a state with J equal to -2. There's only one such state. And then you see now you can act with J plus on this state. And that gives you a 2 here times the state 2 minus 1, which then tells you that I can actually define that as a J plus with a half here. And if I rewrite this one, what I'm getting then is a J2 plus state, which is just the square root of 2, because I can also define that one in terms of the state 0. So I can move, if I act with J plus on that one, I can define the state with Jz equal to 0. And that gives me a square root of 6. And then I can find the remaining states, as this is 2, 1, which is simply the operation of these operators. And then 2, 2 is simply going to be the state here. So that means I can, with these operations here, I know the states. And you see now that if I act on J plus with 2, on 2 and minus 1, I get 2 and 0. And if you go back to the Hamiltonian then, so if we look at that one, the Hamiltonian is now written in terms of these lowering and raising operators. And it's also written, if you go back here, to J plus squared and J minus squared, and Jc for the H0 term. So we have a Hamiltonian which contains Jz, J plus and minus. We have 5 computational basis states. And then we can act on the Hamiltonian. And when we do that exercise, we can then simply, when we construct the Hamiltonian matrix elements for J equal 2, we simply need all these operations here with J plus and J minus. And then if we repeat that, we end up with a Hamiltonian matrix for this specific case, which looks like this. So that's the matrix, is a 5 by 5 matrix, which we can diagonalize. So what I would like to propose, however, when we now move into the our own explicit calculations, is not to start with this J equal 2 case, but start with J equal to 1, which means that we are just going to have J equal to 1. That means we have 3 spin projections, -1, 0, and +1. So what does that mean? So let's go back to the whiteboard and try to draw the states which we will get then. And this is going to define the Hamiltonian for the project, the beginning of the project. And we are going to keep only epsilon and Jz. We're going to take J equal to 1, and we're going to take away the W term in the beginning, just to get started. So that means that the Hamiltonian is just going to be this J plus squared and J minus squared. And we are going to produce a Hamiltonian matrix, which now needs these specific matrix elements. So let's go back to the whiteboard after we've set up the matrix elements. So you're going to get a Hamiltonian matrix, which looks like this. And we have a Hamiltonian, which is now written in terms of these quasi-spin operators. And these are the things which we will encode with the variational quantum eigenvalue, quantum eigensolver algorithm. And I need to detail that one for you. And we will probably need a little bit more time next week as well in order to wrap up what we've been discussing here. So in the slides here, you will also find an example on how you can set up these matrix elements and also use the variational quantum eigensolver, which follows Qiskit. But we need a little bit more time to go through the details properly. So the Hamiltonian, which I want you to take a look at till Thursday when you guys are going to meet, is actually to convince yourself about these type of expressions, and that when you calculate the matrix elements, you do actually get this as a Hamiltonian matrix. And this is something which we can diagonalize easily and find the eigenvalues of. So we have an exact expression when we diagonalize this 3 by 3 matrix, and we can compare our quantum eigensolver with the exact expressions. So if we now go back to the case which we have with J equal to 1, so let me just switch back to the whiteboard, just a small moment here so that we have the basic understanding of the type of system which we have. So let me see, there it comes up. So the case which I went through in the slides were the n equal to 4 case. But what we are going to look at now is a case with n equal to 2. So we have two particles. And our Hamiltonian is now going to simply be given by this epsilon times jz, which we are going to rewrite in terms of Pauli matrices. And then we had this, I think it was 1/2 times v, and then we had this j plus squared plus a j minus squared. So this is going to be the Hamiltonian, and the type of states which we can have now are states of this type. So this term W is actually a term which needs more than two particles to be able to be used. So we would have a state which will be given by this state 1, 2 here, and we could call this phi 0. Then the Hamiltonian allows us to break a pair. So we could now have a state which looks like this. We could call this a phi 1. And you see now that these states here, we have to be a little bit careful in the way they look like, because it doesn't need to be that one. It could also be a state like this. So we have this slot, and then we have this slot here, etc. And then we have an additional state where we now have a phi 2 here, where we have both particles in the upper state here. And these states are going to be states which have a j, total j equal to 1. So remember now that the total j is going to be equal to j1 plus j2. That's the maximum value which we can have. And j1 and j2 is equal to 1/2. So that means that j, in our case, is going to be 1. And that means that jc is going to take values between -1, 0, and 1. So when I use this raising and lowering operators, I can actually start with a state phi 1, which is going to be a state with j equal to 1 and jz equal to 0. So that will be given by j plus acting on this state with j equal to 1 and jc equal to -1. And then we know that phi 2 is uniquely determined in terms of the two spin-up states, but you could actually construct that one by acting on j plus with the state with j equal 1 and jz equal to 0. So setting up the states tells you which states are those which will contribute to your Hamiltonian matrix. And when you go through the algebra, what you will get then, if we now go back again to these slides, and I invite you to do that as an exercise. If you just take this Hamiltonian here for the Lipkin model with j equal to 1 and 2 particles only, then we can rewrite this in terms of these operators, no, these matrix elements here. So one of the exercises till Thursday, when I also have wrapped up the project, is actually to take a look at this specific simpler case. Now, what we need now is to set up the kind of operations which we end up doing on these specific states here. So we need to figure out how to set up the variational quantum eigenvalue solver, variational quantum eigensolver. That's the correct word to use. So let's then go back to the slides here and discuss a little bit about the basic mathematics which is now needed. So we have a Hamiltonian which is written out in terms of quasi-spin operators, and we need to rewrite that in terms of the various Pauli X, Y, and Z matrices. So let's remind ourselves a little bit about the operations which we need to deal with. So we have the next topic now, which is the quantum, or the variational quantum. I always make a mess here when I'm talking about the VQE, variational quantum eigensolver. And this is the algorithm which we are going to implement in order to study these quantum mechanical systems. So what we want is actually to rewrite the Hamiltonian, and I'm going to take some simple examples here. So a typical example could be a Hamiltonian which looks like the following. And this is just an example, a very simple example. So we could have a constant h, a 0.2 here, just a number, which is now multiplied with a sigma x, plus a 0.5, which is multiplied with a sigma y matrix, plus 0.6, which is multiplied with a sigma z matrix. So this is an example of a very simple Hamiltonian, which we can look at. So the thing which we need to figure out now is how do we translate this one into gates and circuits, and how can we use Qiskit, and how can we use this variational quantum eigensolver, which is normally shortened to VQE here. So this is normally rewritten in terms of X and Y and Z matrices. So this is fully equivalent, plus 0.6 times Z here. Now, let me just quickly remind you of the kind of measurements which we are going to do now in order to set up this quantum eigensolver. So the VQE algorithm, in a nutshell, is based on the following. So we have an ansatz, and that ansatz is us preparing the system in a given state. Prepare a parametrized state, initial state. So this could be a state with the qubits in a specific state. Initial state phi, psi. So this is normally called the ansatz. The second stage is the measurement stage. So what we're going to do now is to measure. And if you remember back last time when Stian presented Qiskit for us, he talked about a quantity which is called the number of shots. So the number of shots is actually the number of time we measure an expectation value. So that means that we are going to measure the expectation value. And in our case, this is now going to be the expectation value of this specific state with our Hamiltonian of psi. And we're going to do this many times. Then what we have next, since this is using the variational principle, it means that we're going to minimize. That's the minimization part. And we're going to have parameters. So we're going to tune the parameters. And these are going to be given by angles in the rotation matrices, which are then proportional with the X, Y, and Z matrices. So we tune the parameters. This is the variational part of the ansatz. In order to minimize the expectation value. And the smallest value will be the best approximation to the minimum of the minimum eigenvalue. So this means that we are targeting the lowest lying state with a given symmetry. So we tune the parameters of the ansatz to minimize. The expectation value. Okay, so these are the three basic steps. And when we are setting up the Hamiltonian, then this is actually something which is best explained by the example. And in order to get a little bit handle on this, I'm just going to remind you a little bit quickly about the different operations which we have. So if we now have the sigma x or the x operator, so we know that these have a computational basis. So these are actually the eigenbasis states of this sigma x. This is something which we labeled earlier as a plus state, which is the same as 1 over square root of 2, linear combination of 0 plus 1. And we know if we only have 0, it flips the spin. If we have 1, it brings us to 0. And we have the other state, which is a minus, which is then a linear combination again of these two states, the 0 and 1s, which are the computational basis states, minus 1. And then we have for y, or sigma y, or just y, as I'm often going to label it, we have a state which is I here, which is the same as 1 over square root of 2, and then it has 0 plus I multiplied with 1. And then we have the state which is minus I, which is 1 over square root of 2. And then in this case, I have 1 here, no 0, minus I times 1. And then we have the computational basis states for the Z matrix, where we have 0, which is just 1, 0. And then the other one, which is 1. So these are the computational basis states for these operators. And we know that when I act with C, which is the same as sigma Z, acting on 0, this is the same as 0, so it has eigenvalue plus 1. And then if I act with the same sigma Z acting on 1, this has eigenvalue minus 1 multiplied with 1. And similarly, if I take sigma x acting on this state plus, this gives us plus 1 multiplied with the state. So this has an eigenvalue equal to plus 1. And similarly, if I take sigma y, this is just to repeat some of these operations which we have seen before. This is now given by I here. And if I take sigma z acting on 1, this is the same as minus multiplied with 1. So in order to prepare things which we're going to do now, it's useful to actually look at the expectation value of one of these operations here. So we could think now of measuring the expectation value of the sigma c state. So what we could do then is simply to assume now that we have an ansatz of a state, which is given by some alpha 0 of multiplied with 0 plus alpha 1 multiplied with a basis computational state 1. Then what we want now is the expectation value of psi of sigma z psi. And when I set up the calculations here, this is simply going to be alpha 0 complex conjugate 0 plus alpha 1 complex conjugate of 1 . And then we have the sigma z matrix, which in this case is simply 1, 0, 0, minus 1. So this is our sigma z, which is also equal to this is quantity z, as we called it. So I'm gonna switch between z and sigma z, depending on the context, but it's common to see this one as just a z operator. And then we would have the state alpha 0 multiplied with that one, minus plus alpha 1 with 1. And then we know that when sigma z acts on the state 1, it produces a minus sign. So this is nothing but alpha 0 squared minus alpha 1 squared. So note the minus sign. And the way we typically do this is to produce n measurements. So we would perform n measurements. And these n measurements can then yield a number for alpha 0. So which then could be something like n0. So this is the number of times we measure alpha 0 divided by n. And similarly, we can then have alpha 1 squared, which is now given by n1 divided by n. So our actual calculation here, when we now are setting up, or if we perform a measurement of z or sigma z, this is simply going to be given by n0 minus n1 divided by n. Now, clearly, if we have a 50% n0s and 50% n1s, then this should give us just 0. What you will see when you run these experiments on a quantum computer is that you don't get exactly equal to 0. So this means that if you prepare the state, so if we now take as an example, suppose now that we prepare the state in a state 0. Suppose we start. So this depends very much on which kind of state the initial state was given in. So suppose we start with 0, and then we act on this one with a Hadamard gate. So what we do now is that we perform a Hadamard gate operation on it. And that means that we have 1 over square root of 2, or 1, 1, 1, minus 1, acting on 1, 0. And we know that that simply gives us the state, which is now in a new state, where you see that we have only 1s times 1. So we actually get 1 over square root of 2, and this is 1, 1. So this is 1 over square root of 2 of 0 plus 1. And this is the state which we call plus. Now, if I then measure this one, and suppose now that we make measurements, so our measurements give now that this alpha 0 squared is approximately equal to 1/2. And then alpha 1 is approximately equal to 1/2. Then the expectation value for this specific state which we have prepared of the sigma z operator is actually equal to 0. And that is what we should measure. If we, on the other hand, apply yet another Hadamard gate, so suppose now that we do 2 Hadamard gates, h times the state 0. This is the same as, and now remember, this is the same as identity matrix times 0, which means that we just get 0. So when we then perform the measurement, we are just going to get 100% for alpha 0. So that means that this alpha 0 squared is simply going to be equal to 1. And obviously alpha 1 squared is going to be equal to 0. And that means that this measurement which we make with sigma z on that specific state is equal to 1. Now, when we now are constructing the Hamiltonian, what we are going to do then, if you now think back to the Lipkin model, and we look at this specific Hamiltonian which we have here, this simple example, the one which we put up here, this is now a Hamiltonian which we can simulate with the VQE algorithm. And the thing which we are going to discuss a little bit more next week, I see that my time is running out here today, is actually to set up the expectation value with a specific ansatz. So we will wrap up the definition of the VQE algorithm and how to actually perform the calculations of the Lipkin model Hamiltonian. So what we would need then, if we now go back to this specific Hamiltonian, is that we have a state psi, which we have prepared. which in this case would simply be given by psi, if we look at the simple model of sigma x plus 0.5 of sigma y plus 0.6 times sigma z here, multiply with psi. And then what we end up with then is just a series of measurements in terms of sigma x, sigma y, and sigma c operators. And these are things which we can then translate into circuits where we perform these explicit operations and then perform a set of measurements. So next week, what we're going to look at then is how do we set up this specific set of measurements and how do we perform the calculation. So I see my time is running out. So for you guys, when you're going to meet on Thursday, I should then have been able to wrap up the project description. One of the things I would like you to do is actually to go through this material in the Lipkin model and convince yourself that the kind of equations I put up make sense. And then if you wish to, you could already start to look at how you can encode this in terms of specific gates. In the slides this week, if you scroll down, so let me just bring this up here. So if you scroll down on the slides for this specific week here, you will actually see examples on how we can set up. So the first case is actually us diagonalizing that simple Hamiltonian. And then the next step, which if you scroll down after this Hartree-Fock intermezzo, is actually how we would set up the quantum circuits. And in our case, the Hamiltonian now takes the form when we have these specific expressions in terms of a Z1 gate, and then we have an X1, X2, and Y1 and Y2. So these are Pauli matrices, which we then use in order to set up the Hamiltonian. So I just want you to convince yourself that you can actually, with these expressions, you can go straight into the definitions of the Pauli matrices and then set up the final Hamiltonian. And then we would have a ansatz, which we can set up, which would then depend on parameters. And then we are going to discuss in more detail next week how we arrive at this equation. And that should hopefully give you enough material to get started. And please feel free to take a look at the material which you have here. And as I said, next Monday, I will wrap up this discussion. And then hopefully we have enough material to be able to study some of these simpler quantum mechanical Hamiltonians. Feel free to ask questions, guys. I'm going to stop the recording here.